Okay, good afternoon. Thanks for joining everybody. Um, I'm teaching a course currently that includes scanning electron microscopy, which is, of course, an electron beam that hits a specimen and gives off electrons. And it it is great preparation to learn about that in order to extend those concepts into electron beam lithography, which is usually the intent of the course. But this year I separated out the e-beam lithography material from the scanning electron microscopy material so that we could make this special lecture. So I am Professor Gary Bernstein at the University of Notre Dame, and I will do the first part, which talks about electron scattering and various dependencies and ideas that I think beginner e-beam lithography users should have in their heads so they can interpret the results that they get. If it isn't what they wanted, they'll be able to look at the results and make some kind of intelligent decisions about what they might have done wrong. And Dr. Gergo Jacquemani, research um, scientist at Notre Dame, is an extremely skilled and knowledgeable practitioner of electron beam lithography. And there's nobody better, in my opinion, than him to tell you about the nuts and bolts of using the Raith system here at Notre Dame. The total length of the two combined talks, we've allotted 90 minutes. Hopefully we won't go that long, but that's what we've scheduled for. So I'm going to start now with some background material. I'm going to talk about electron scattering in electron beam lithography. I'm going to talk about the ultimate resolution of electron beam lithography, what basically limits you from getting any smaller than a certain feature size. I'm going to talk about how beam energy affects exposure dose. I'm going to talk about what you're doing when you align one pattern to another pattern, what those electrons are doing, what kind of detector it is, what decisions you might make when you design alignment marks in terms of electron scattering, not the design of the alignment marks. I think actually Gergo is going to talk about that. And proximity effects, big issue if you're making dense patterns, how the electrons affect various regions around wherever the beam happens to be. And that's what the word proximity means. It means nearby. Okay, so what is electron beam lithography? In fact, I'm only going to talk about PMMA negative resist. I'll bring up a couple other resists later, but just in passing. And PMMA, polymethyl methacrylate, is basically plexiglass. It's dissolved in a suitable solvent, and you spin it on and you bake it. And it's really just a plastic layer on your wafer after you spin a thin resist coating. Now, PMMA is a polymer. It has long polymer chains with very high molecular weights. For example, 960,000 molecular weight of one molecule is the most common molecular weight that is used for high resolution electron beam lithography. And when the beam hits it, the electron beam chops up these long polymer chains into smaller polymer chains. And then in a suitable developer, the developer can latch on and remove the smaller polymer chains more easily than the long polymer chains. In fact, in suitable developers, you can soak it for a long time and see virtually no change to the unexposed resist. And so this is a picture that kind of illustrates that: big pieces of spaghetti and then smaller chopped up pieces of spaghetti. And when the beam moves around, the energy from the beam, in a way that I'm going to explain, breaks the bonds and chops the long polymers into smaller pieces. This is an overview of generally how that's used to make a pattern in electron beam lithography. You have a substrate, you've got, well, some kind of, forget the epitaxial layer here. You put an electron beam resist on it. I'll be talking about PMMA mostly. The electron beam goes in and makes those exposed regions more soluble in the developer. That is the definition of a negative resist. And in a suitable developer for whatever that resist happens to be. You remove the exposed layer for the negative resist, and then you can continue the processing. And Gergo is going to talk a lot about liftoff. You deposit metal, and then you remove the resist. And when you're done, you've replicated the electron beam pattern in a metal pattern that is on your wafer. Of course, you could do wet etching, you can do dry etching. It depends on what kind of resist you're using to know how well it will stand up to dry etching. But besides that, the important thing to know is that the beam makes a small pattern, and I'm going to talk about what affects the resulting pattern based on the exposure that you do. So this picture shows where the electrons go. This is the beam. This is a narrow arrow. That's the beam of electrons. And in the Raith system, I would estimate it's around 2 nanometers, say. I don't know exactly, 2 to 3 nanometers. It depends on your beam conditions. And the electrons are 100 kilovolts in the Raith system. They enter your resist or substrate, whatever you've got as a stack, and they bounce around and they reemerge, as some of them reemerge as backscattered electrons. So we're going to talk about 3 kinds of electrons. We're going to talk about primary electrons. We're going to talk about those high energy primary electrons that manage to find their way back out again with a little less energy than what they went in with. Those are called backscattered electrons. And all along the way, energy is given off by these high energy electrons, and they create low energy secondary electrons. So scanning electron microscopy most often uses the secondary electrons to create the pictures that you get when you image your nano devices after you've made them. You probably don't use backscattered electrons for imaging, but you can do that too. So the secondary electrons are really important for the exposure of the resist, and the backscattered electrons are really important for proximity effects. I'm going to talk about all those things. Whoops. So this is a picture that shows literally solid block of PMMA, and it shows how the electrons go in and where they give off their energy. So this is an exposure with an electron beam. It's a very old picture somebody did once a long time ago. And then after developing for various amounts of time, and it reveals where the energy was deposited in the material. What you want to get out of this is that when electrons go in, they generally deposit their energy like this. But when you have PMMA or any resist on the top surface, it's a very thin layer. And we're only really interested in the energy that's deposited in the very top layer of whatever stack that you've got. So let's talk about the exposure dose dependence on the beam energy and limits to resolution. This is my favorite equation. I think it's one of the most important equations in all of electron microscopy and scattering discussions about electron beams and solids. It's called the beta equation, otherwise called the continuously slowing down approximation, CSDA. So I like to call it the continuously slowing down approximation. But anyway, what this equation says is that the change in energy of an electron as a function of the distance that it's moving through the solid, you want to have this picture in mind. S is path. S is the distance along this path. And it says that the electrons lose energy per distance at a rate equal to this equation. So the important thing to see about it from this equation is that the higher the atomic number of your material, the quicker it loses its energy. So it's losing energy more quickly. It doesn't go as far through the material when you have high atomic number material versus lower atomic number material. But you might intuitively think that the higher the energy of the beam, or the higher the energy of the electron at any position within the solid substrate, the more energy it would lose per distance. Well, that kind of makes sense, but it's wrong. this equation basically says that the higher the energy, the less energy is lost per unit distance. And that does make some sense if you think about the electron interacting with atoms due to Coulomb forces. They spend less time at higher energy in the vicinity of the nucleus or within the electron cloud, so that they don't have as much chance to lose energy. And when they eventually do lose energy a little at a time, and they slow down and they have less energy, they are then affected more by the scattering mechanism, and they lose energy at a faster rate the lower the energy that they have. Really important. This affects so many phenomena in electron beam lithography that you really need to know this this relationship. Now, E appears in two places. One is within this natural log, and one is in the denominator of the equation. And the natural log is not a strong dependence. So let's just say that the rate of energy loss goes inversely as the energy of the electron. Don't get E confused with the beam energy. It's the beam energy just when the electrons enter the solid, the top of the resist, but as it works its way through the resist and then through the substrate, it's losing a little energy at a time. And the amount of energy that it loses is its energy at that particular point along the path. Okay, so now you understand that energy is really important in terms of how much energy that it loses. So one implication for electron beam lithography is that higher energy electrons lose less energy per distance. Therefore, you need a certain dose at higher energies to expose resist that is a higher dose than at lower energies, because you can't expose resist unless some electrons somewhere give up their energy and do something to those bonds to break those bonds, or whatever it is they're going to do chemically to expose the resist. And since there's very much less change in energy at high energies, you just simply need more electrons to affect those changes in the resist. So in general, resist sensitivities go down as energy goes up. So do you have a choice of energy in the Raith system? No, you do not. But you will be reading literature and you'll be seeing various resists and various exposure doses. And when you do, just be aware that if it was done at 50 kilovolts or 75 kilovolts or in an electron microscope at 30 kilovolts, those doses will vary considerably compared to what the dose that you're used to using for 100 kV electrons. So secondary electrons are generated throughout the resist layer and throughout the substrate, but I'm concerned about the resist layer everywhere the electron beam is. Now, the lower the energy of the electron, the more secondary electrons will be generated per unit length, because that is one way in which the primary beam is actually losing its energy to the substrate. So the primary beam creates secondary electrons, and secondary electrons are really low energy. So the energy of a secondary electron is on the order of a few electron volts, say 10 electron volts, maybe 50. And there are some secondary electrons that go all the way out to like 1,000 electron volts of energy. Volts and electron volts are potential. Volt is potential, electron volt is energy, but they're related through the force on the electron. So anyway, the primary beam is high and the secondary electron energy is low. But if we think back to the beta equation, we know that an electron loses more energy the lower its energy, basically. So which one is going to be losing more energy per unit distance? The primary beam at 100,000 volts, or secondary electrons, which range anywhere from a few electron volts to up to even a few hundred electron volts or so? And the answer is the lower energy electrons are actually losing much more energy per unit distance than the primary beam is. And that loss of energy by the secondary electrons is what breaks your bonds. So it might surprise you to know that your beam is not actually exposing the resist. The beam is creating secondary electrons, and those secondary electrons expose the resist. So it's an important thing to keep in mind because we're going to talk about in a little while the ultimate resolution that you can expect to get in resist because of that particular phenomena. Before we go there, we need to talk about contrast of a resist developer system. This is a plot. If you've never seen it before, it's a resist contrast plot. And what you do is you take the resist thickness, you normalize it to whatever its thickness is, you call it 1, and then you plot after exposure and development with your favorite resist, your favorite developer, at your favorite temperature for your favorite amount of time. That gives you one curve. The curve could be different if you change any of those things. But for the way that you do a development, you get one curve. So here's the curve. And if the dose is too low, it basically has no effect on the resist. And then you start to see, oh, I've exposed it for this amount of time. I develop it my favorite way. And it starts to get a little thinner and a little thinner with more dose and more dose and more dose until ideally you get to a point where you have cleared all the resist. You don't want any resist left on the surface of your chip after you've done your exposure. If you even have a few nanometers of resist left as what I like to call a scum layer after you've done your development, that is a bad thing. That can cause your metal to delaminate, if not during liftoff, then later. If you heat it, it'll turn into charred crud. So you want to make sure that you expose your resist long enough that you have definitely cleared all of it. So the distance in which you want to go in dose further than the bottom of this curve. I've done a lot of this, and there's a lot of data that shows like scum layers until it really settles down. You want to make sure you're even past this dose, which clears it. So anyway, the slope of this is called the contrast. And the higher the slope, the higher the contrast. And what this basically says is that if there's really high contrast, then your developer can tell in a very tiny difference between not exposed enough and exposed enough. The lower the contrast, the much greater difference in dose there is between starting to develop your resist and finally clearing all of your resist. High contrast is better because regions close to each other will have only small differences of energy deposition, of dose. And if you want to distinguish one region from a region right next to it, then you really need a high contrast developer. So you need to be aware of the properties of your resist and where this exposure dose lies that clears it, and what its contrast is, and what the developer is you're using, and how you're going about using your developer and getting the most contrast out of your resist. So if it's really critical for you for doing dense, very small features, I recommend that you become familiar with this and start to learn more about the resist developer system than you might know at this time. So here's an example I got off the internet of real data. I've done this many times, and you can see here that there might be some residual resist in this region. So to be safe, you want to be out here. There are 4 different resists represented on this particular plot. PMMA is one of them, and PMMA is here. What I want to point out in this plot is the beta equation, the continuously slowing down approximation, and how you can see it at work in this plot. This is the exposure dose for PMMA at 30 kilovolts. I don't know what the developer is. And this is the exposure dose at 75 kilovolts. And the difference between where it just starts to clear at 30 kilovolts and where it starts to clear at 75 kilovolts is about a factor of 2 in dose. Well, if you look at this equation, it turns out that plugging in 30 kilovolts and 75 kilovolts gives you a factor of 2.2. So this equation very nicely predicts that your energy loss of your high energy beam electrons as they're losing energy to secondary electrons, which then just immediately break the bonds in the resist, is a factor of 2. And so it works very nicely. I'm just using this as a demonstration to try to convince you that this is a valuable equation. Okay, and now let's talk about how fine of a line do you think you can get if you expose a single line of PMMA and then you develop it? Do you think you can use a 2 nanometer beam and get a 2 nanometer wide exposed line and maybe even lift that off and get 2 nanometers? And this paper was done in 1983 by David Joy. And when I discovered this paper, I thought, oh, wow, this explains a lot. This really explains the limitation of what you can reasonably expect to ever get out of your E-beam system. So this assumes that the beam has 0 width. If your beam is 5 nanometers wide, you can just add 5 nanometers. Not exactly, but just go ahead and add 5 nanometers to this discussion. So what this says is, because it's the secondary electrons that actually do the exposure, and there are a lot of figures that I'm not showing you, those secondary electrons deposit kind of a constant amount of energy out to a distance that's about 5 nanometers away or 10 nanometers away. And you need an extremely high contrast developer resist combination to be able to distinguish this dose from this dose if you think you're going to remove all of this material to the left and not remove all the material to the right. So for reasonable resists with a reasonable developer and contrast, you pretty much are stuck with this fairly uniform energy deposition for a distance of 5 or so nanometers. And this, to me, explained why, for dozens and dozens of papers that I had seen many years ago about E-beam lithography, nobody ever reported any single line that was less than 10 nanometers in PMMA. So it's good to keep in mind what really is going to limit your dose for a single isolated line. Now, for lines that are very close to each other, the problem gets even worse in ways that I'm going to talk about in a little bit. By the way, this is some data that my graduate student got years ago, and you can see that there is this tendency to have residual molecules on the surface left over, and you really need to get out beyond where this sloped line extrapolates for the contrast level. Okay, I'm changing topics quite a bit right now. I want to talk about the alignment marks, the fiducials that you have that you need to align one layer to the next layer. So this is imaging fiducials or alignment marks underneath resist. So your fiducials are underneath your resist, and we need to have a short conversation about backscattered electrons. So as a reminder, here's your primary beam, and they rattle around inside your substrate. This is not a resist layer. I should have deleted this from this picture. Ignore the 5 lambda in this dashed line. You have some resist on the surface, and the primary beam electrons go in, and they backscatter, and they come out. If there's a layer of metal underneath the resist, they'll hit that layer of metal and they'll be backscattered out. And we want to talk about that. So first I want to talk about, so these are backscattered electrons. And I want to talk about what a backscattered electron detector is, because it's quite different from a secondary electron detector. I don't know with 100% certainty what's in the Raith system, but it very well could be this kind of detector. Underneath the pole piece, above the specimen, your sample, is basically a solar cell, and it's a PN junction. And when backscattered electrons come back off the surface and they hit the solar cell, they generate electron hole pairs. You read that signal, and you can tell how many backscattered electrons that you're getting. And this is important for the alignment mark. Let me also point out that the higher the atomic number along this axis, the larger is the backscattered coefficient eta. And eta is the ratio, the fraction of total number of backscattered electrons to primary electrons. So for high atomic number material, lots of the primary electrons eventually rattle around and find their way back out of the surface as backscattered electrons. And for low atomic number material, low Z material, fewer do. And this is the underlying phenomenon that makes it possible for us to have alignment marks in the Raith system. This is something that I did years ago, and it illustrates that point very quickly. These are silicon dioxide spheres that are about this much radius, 450 nanometers. And this is a low energy image, 3 kilovolts. And they look like they're solid spheres of something. But when I raised the beam energy to 30 kilovolts, it reveals that inside the center of these spheres was a small gold nanoparticle. So at low energy, we couldn't see the gold nanoparticle anywhere. We only saw the surface. But when we used 30 kV, those electrons went in, they hit the gold, and for reasons I won't get into right now, they generated more secondary electrons on their way out. That is a phenomenon, but it's not what I'm talking about here. What I'm trying to tell you is that the backscattered electrons generated information by ricocheting off of these gold centers, and they became visible. So this is my best example of this kind of thing. So Gergo, an expert at simulations, was kind enough to do some Monte Carlo simulations for me. And every one of these pictures that I'm going to show you is the exact same size scale. So this shows silicon with the proper amount of PMMA on the top, which is low atomic number and has virtually no effect on any of this that you're seeing. And the primary beam comes in, and these electrons scatter around, and they lose energy, and they stay in the substrate. Of course, current flows through the substrate because it's conducting. And the red lines are the backscattered electrons. So immediately you can see that the backscattered electrons emerge from a very wide region compared to where the beam goes in. But this number, backscattered electron coefficient of 100 kV electrons on silicon, ignoring the PMMA, is 0.0886. So about 8%, 9% of the electrons that go in manage to find their way out. This is PMMA on gold. So there's a thin gold layer underneath the PMMA. It's right here. And relative to this size scale, it's really tiny. But look at what happened to the backscattered electron coefficient. It went up by quite a large fraction. It went from 0.09 to 0.11. And so the backscattered electron detector can easily detect that difference in the number of backscattered electrons that it's picking up a signal to because of a 200 nanometer gold layer that's on the surface. And that means that you can put down your fiducial mark of, say, 200 nanometers of gold, spin resist over it, and as long as you're using a backscatter detector, you can see your gold alignment marks. They're just visible through the resist, just like my gold nanoparticles became, they weren't mine, became visible through this very thick silicon dioxide outer layer. Okay, so that explains a really important aspect of what makes it possible to even see alignment marks. But I want to caution you that if you use another kind of material, for example, aluminum is atomic number 13, silicon is atomic number 14, and Z is, for all intents and purposes, the same. And when the beam scans over an aluminum alignment mark, there aren't going to be any more backscattered electrons than there were over the silicon. So you have to be very cognizant of what metal or material or feature or whatever you're using to make an alignment mark and understand its effect on backscattering to know whether or not you're going to be successful at being able to see that alignment mark in the Raith and let Raith do its thing with regards to that alignment mark. So hopefully you you have a better idea from an electron scattering point of view what you're doing when you're doing an alignment in the Raith system. Okay, now about proximity effects. If you're only making large patterns or you're making small patterns that are very far away from all the other patterns, this will not be important to you. But if you're making any patterns that are nearby any other patterns, they're talking to each other through backscattered electrons all the time. And one pattern exposes the other pattern, and that pattern exposes the first pattern. And even a rectangle, every part of the interior of a rectangle is being exposed by other parts of that same rectangle. And those are called proximity effects. So what causes proximity effects? Here's another equation. It's RKO. This is a distance. It's called the Kanaya-Okayama range, RKO, and it depends on the energy. It goes up very strongly with the beam energy, and it goes down approximately as 1 over the atomic number. And what this equation basically says is that the distance that electrons penetrate into a substrate is 90% of the distance is RKO. Now, those backscattered electrons come back up from the top surface and go out a distance about 1/2 RKO on each side. So the communication of the electron beam is really large because this is 23 microns right here. There are a lot of backscattered electrons from near the beam that go a long way away and can expose other patterns from the bottom side coming out as opposed to your beam, which is exposing it from the top side going down. And that's what this represents. And the distribution is generally regarded to be a Gaussian with some half-width beta. And beta is generally taken to be RKO over 2. So it's like you take this distance, turn it sideways, and put it here. Okay. There are some numbers here which I'm just going to skip, but I do want to do a comparison between silicon and gallium arsenide. So the backscattered, not only does where the electrons come out depend on 1 over Z. In other words, higher atomic number substrates cause the backscattered electrons to come out closer to your beam than the low atomic number substrates would be further from the beam. But as we already pointed out, as I already told you, low atomic number substrates have fewer backscattered electrons, and higher atomic number substrates have many more backscattered electrons. So if you do an exposure on a high atomic number substrate, not only do you get many more backscattered electrons, which are bad for proximity effects and causing you a lot of trouble, but they're crunched together in a more confined region. So the density of those backscattered electrons goes up more like a factor of 4 than anything else. So proximity effects get much worse depending on the substrate that you're doing your exposure on. Now, it so happens that the work that I was doing when I made this slide many years ago, I was making devices on both silicon and gallium arsenide. And so I use these 2 numbers, but you could be working on anything. And if you've got epitaxial layers and you've got a stack and you're concerned about this, then you want to put them into a Monte Carlo simulation and try to get some representative numbers that will help inform you about what you should be doing. Okay, so this is kind of a repeat of everything I just said. I apologize for the bad handwriting and everything. But as a review, I've got pattern one and I've got another pattern over here, pattern two. So when I'm exposing pattern one, those backscattered electrons will zip through pattern two, and those secondary electrons, etc., will add exposure dose here that I may not have calculated when I simply assigned an exposure dose to this pattern. So all the patterns are affecting all the other patterns if they're anywhere in the vicinity of each other. Higher primary beam, same total eta, high RKO, so larger area of backscattered electron return. So let's look at these Gaussian distributions for low KV and high KV. For low KV, you get the same number of backscattered electrons, but they're generated more close to the beam. And high KV, they're spread out over a very large distance. At 100 KV, that distance, depending on your substrate, could be 20, 30, 40 microns away and be pretty uniform and be pretty small, low background concentration. And what that means is that you'll give some background dose if your pattern is small, but it won't be lumped up in any particular area. It'll just raise the background distribution, so that lowers the amount of dose that you would need to expose those regions. Now, when you have, if you want to compare the atomic number of the substrate, then for high atomic number, they're more crowded in the vicinity of the beam, and that will make even a smaller pattern region be more affected by these proximity effects than the low Z, which is spread out over a very wide distance. So on silicon, you might be okay with 100 kV, depending on the size of your pattern, or not. You just have to look at your pattern and see what happens. So this is kind of the same thing. This is an old picture from an old book. I don't really like that picture. So the background dose is basically raised up. And if you don't account for it, then for the same developer combination, you'll end up with wider patterns than you thought you should have based on your actual exposed region. So proximity effects cause patterns to bloom out because of this background dose that raises the effective dose that you've put into your substrate. Now, a bunch of things can happen. So if you see this happening in your pattern, then you need to understand what's causing it and what you need to do about it. And Gergo can tell you more about running proximity effect correction software at Notre Dame. But this is what that works to try to correct. So there are two names for proximity effects. Interproximity effects, a little artificial, but it's helpful. That means if I have one pattern and another pattern, they affect each other. So this dose exposed this region, this dose exposed this region, and this dose exposed this region, and in general, you had too high a dose, so this got larger. So this is called interproximity effect because they're two separate patterns. But intra-proximity effect is I've got one pattern, but it doesn't come out the way I want it to be. So why would these corners not be exposed, but this region be exposed, and this region is even well, that's overexposed because of this, but here it's only exposed properly to this edge. And that's because every region within this rectangle is exposing every other region within this rectangle. And if you think about it, if all you made was this rectangle, then this corner is not getting any backscattered electrons from 3/4 of the quadrant around it. It's only getting backscattered electrons from this region into here. But this region here is getting backscattered electrons from all around it, so it's going to be exposed enough to develop. So can you just reason this out? Well, yeah. If you are having problems where your corners aren't square enough, you could go in and expose another rectangle, and you'd be doing your own proximity effect correction effectively. Or you can run the fancy software that Notre Dame has. And this is a good slide to refer to. Gergo ran this simulation because I don't think this data was available in any of the books that I saw. So it's good reference material. It shows you this backscattered coefficient all the way out to 100 kV. And the data that I have available says it's basically constant, same backscattered coefficient as a function of energy, but the data only goes out to 50 kV. So yeah, it's fairly constant. But Gergo's simulations show that it continues to drop, going all the way out to 100 kV. So this might be useful for you if you get these slides. All right. So to bolster this, I took this simulation here, which what you already saw was PMMA. And if you look, the size scale of the pictures I'm going to show you is exactly the same. This is PMMA. This is silicon. And this is gallium arsenide. Now, this is to scale. These are exactly the same size regions. So look at the region over which these backscattered electrons are coming, and the backscatter coefficient is 0.09. And here, the backscatter coefficient is 0.24 on gallium arsenide, and the region is vastly smaller, but many more backscattered electrons. So this picture and this picture, which I show, these are distributions as a function of distance, and all I did was I just made a line to just sort of show its shape. And what it basically says is that on silicon, you get the backscattered electrons over a much wider region and at a much lower amount than on gallium arsenide, where they're much higher and they're much more concentrated near the beam, which means much more concentrated in the region that you have multiple patterns that can be damaged by the backscattered electrons. Okay, I'm almost done. I think this is my last slide, as a matter of fact. The purpose of this slide is to say, well, what if we take lines? We just want to make very narrow lines, and we put them closer and closer together. And we go back to this discussion about the role of secondary electrons and how they expose the resist and what their range is and where the secondary electrons deposit their energy. And this is that same paper. And if you're really interested, you should get this paper. It's really worth reading. And if you have an isolated line, well, you are free to develop this as best you possibly can and make one narrow line. But if you have a bunch of lines together, you're going to get exposure between the lines. So an isolated line, this is related to the proximity effect of two lines, this line and this line next to each other. And because they communicate with each other through backscattered electrons, the dose will be raised up. This is on silicon, this is on gallium arsenide. And, that's tolerable, and you could develop these out. There's a fair amount of difference between these doses, and you have a high contrast developer, you can get away with it. But if you start making them closer and closer together, the contrast, the modulation between these lines gets lower and lower, which means your developer and resist combination has to work harder and harder. It's got to be better and better to be able to develop out just where the dose is highest and not where the dose is lowest. So the closer these lines get together, the less the modulation is. This is at 30 kV, and this is at 50 kV, and it's somewhat better if you look at this. Notice that this doesn't have very much modulation from exposed to not exposed. But here at 50 kV versus 30 kV, there's more modulation between exposed and not exposed. So you have a better chance at the high energy of being able to actually separate out in your development these three lines done here at 50 kV versus done here at 30 kV. And of course, your choice of resistant developer and how you do it is really critical in all of this. Okay, that is actually my last slide. And maybe I can take a couple questions. You're being recorded, and this will be made publicly available. I can take questions. I'll tell you what, anybody who has questions, just contact me by email. I would be happy to answer any questions later. I'm going to turn it over now to Dr. Gergo Jacquemani, research scientist at Notre Dame, and I consider him to be one of the great experts on electron beam lithography for nano devices.
All right. Hello, everyone. So I'm Gergo Jacquemani. I'm a research scientist at the Electrical Engineering Department. And do you see my screen? Okay. So I'm going to talk about like some best practices for using the electron beam lithography system here at the Notre Dame Nanofabrication facility. So Professor Bernstein already introduced to you about the electron beam lithography system. That it's a pattern, it's a direct wire lithography that uses focused electron beam to transfer pattern into a resist, and then to transfer this pattern later on onto a substrate, either by metal deposition or etching into the subsequent substrate. Now, if you know how an SEM works, you already know like 90% how an electron beam lithography system works. It's basically just based on a very fine position of the stage, and also the very high frequency blanking of the beam to expose the resist to areas where you want to have your pattern, and blank the beam to areas where you don't want to have the beam. Now, Notre Dame has a very long history about having a electron beam lithography system. The first system was an SEM, an M-ray SEM that was converted by Professor Bernstein to an electron beam lithography system. This tool was for a fairly long time, the E-beam tool at Notre Dame. It had a 50 kilovolt acceleration voltage, and it can do it was able to do like about like a 30 to 35 nanometer line width with a 60 to 80 nanometer pitch. For a brief time, one of the Hitachi SEM that is in the clean room was converted to an electron beam lithography system with a 30 kilowatt acceleration voltage capability. And then one of the real electron beam lithography system that was dedicated, that was actually built for an electron beam lithography system was the Irion 7700. This system had a 75 kilovolt acceleration voltage, and it had a 6-inch precision laser stage. We did one very fine samples. I think around 10 to 15 nanometer lines were able to write. The current system that we have Notre Dame, it's there since 2011. This is a Raith EBPG-5200. Now, this system is equipped with 3 acceleration voltages, 50, 75, and 100 kilovolt, but it's pretty much exclusively set up for 100 kilowatts. You heard from Professor Bernstein's presentation about the advantages of using 100 kilowatt, that it has less proximity effect. The beam can be very narrow. The only disadvantage is that it requires a higher dose, which means like longer exposure. But other than that, there isn't really any reason why you want to go to 50 and 75 kilowatt. Now, I know that if you have a very, very, very good reason to use one of these voltages, they can set up the system, but it requires like a few days to wind down the voltages to stabilize everything in column and set it up. You will make a lot of other users keep up on their work, because it's not just a simple changing like beam current. It actually takes a lot of work from the lab step to change the acceleration voltages and to stabilize the system. So in pretty much exclusively, everybody uses this system at 100 kilowatt. Now, this system has a 20-bit pattern generator, which means that it can do a very fine step size in the grid, as I'm going to talk about it. And it has the ability to handle up 200 millimeter wafer size as well. from very small chip sizes. Now, if you haven't seen the e-beam lithography system, this is how it looks like. This is the Electron column. Here is your load lock and the insertion rod. This is where all the different tables live, where you can insert different patterns. So substrate. So as I said, like small chips, small wafers, masks, and even up to like a 200 millimeter wafer as well. Now, I want to just tell you that I will tell you a lot of information about how to use the system, but this is not a training. So if you are not a user yet of the electron beam lithography system, this presentation will not authorize you to use the e-beam lithography system in the NDNF. You need to contact Fei Cheng to get a proper training and be authorized to access the system. Now, in order to do electron beam lithography, there are a bunch of different steps that you have to consider. The exposure itself, this is the last step pretty much, and usually that is the shortest amount of time, depending on how large your pattern is. So what normally you have to do is you have to have a CAD program where you design your pattern. Then this pattern needs to convert it through different software to set it up as a job file that the e-beam understands and be able to expose. Then you also have to prepare your sample, like spinning resist. If you have a substrate that is very insulating, you need to do some other preparation to avoid charging. Then comes the exposure, and then you have to develop the pattern to the exposed pattern in order to get this pattern transferred to your substrate, either by metal deposition or some other etching processes. So I'm going to go through most of these steps and telling you that what I think it's like an important factor that you have to pay attention when you doing electron beam lithography. Now, the first thing is to create your pattern. There isn't really any important part on this one. There is the K-Layout software, which is free and easy to use software. You can go online, download it onto your computer. It runs on Mac, PC, and 99% of the cases when you work in a university environment, this software is sufficient. If you want to go very complex layer, then Notre Dame has a license for Cadence. I don't really recommend it if you are a new user and you just need like a 1 or 2 layer layout. K-Layout can handle everything, but just to let you know, Cadence is an industry standard for IC layouts. It has actually way more capabilities than just doing simple layouts for electron beam lithography. We have that, but probably everybody can work with a simple K-Layout design to draw your patterns. Now, once you draw your pattern, that's what you want to expose in the e-beam system. This pattern or this file needs to be converted to e-beam readable files, and there is and also you need to, in the meantime, when you converted the files, you assign different doses. You have to tell the machine what beam current you want to use, and if you do proximity of correction, then you have to set that up as well, so different regions of your pattern will receive different doses. You can also create like fracturing your pattern that tell the system that which order the e-beam will expose your samples. So in order to do that, from your layout editor, Cadence or K-Layout, they're usually using a proprietary file system that you cannot really input to anything else. However, each of these software allows you to convert the file to GDS. Now, GDS is a graphic data system It's a binary file format, open source. It is an industry standard to move patterns between different software and packages. So your first step is to find out how to export your pattern to a GDS file from Cadence or K-Layout or any other layout editor that you are using. Now, once you have this GDS file, you have to set it up which the pattern where the eBeam system will understand it. And for that, Notre Dame has one floating license called the layout beamer. This is where you condition your eBeam pattern. Here, where you are setting, you make your fracturing of your pattern, you set up your dose, you select your grid size, your main fields and subfields. These are all information that I'm going to tell you about what these are. And so basically, this is where you can set up your approximate correction. So this is a file that will transfer your pattern to an eBeam readable file. And this is this GPF file that contains this configuration that tells the Raith system that how to interpret your GDS file during the exposure, basically. So it just the layout beamer outputs this GPF file. And finally, you have to create a script file where you tell the eBeam system that on which part of your sample you want to be exposed the pattern. And also, if you have different alignment, it contains the information about alignment marks. And this job file is basically a script file that tells the eBeam system that what sequence to run certain parameters. Now, when you start layout beamer, so you already draw your pattern, exported GDS, and now you have to transfer this GDS file to a GPF file for the eBeam system. The first thing that you have to do is import your file. And if you just only have one layer, then you don't have to do any extraction. But most likely, many of you will have multiple layers on top of each other that requires different exposures. So for example, if you make some junctions, transistors, or something else, you cannot just do one single layer. And sometimes you even have to work with optical, lithographically fabricated bonding pad structure, and then fabricate your nanoscale devices on the chip. So usually you have to extract the layer which layer you want to expose. Then you can do like a healing, which I'm going to talk about what it does. It removes overlap and fracturing. It's just a good thing to do that. And then export your file to a GPF file. This is where you set up most of the beam parameter, eBeam exposure parameter like grid size, field size, etc. Now, this is just the very minimum that you can do with layout beamer. You can add your proximate effect correction if you want to in this tree. You can be very fancy and just drag and drop like these different forms. You can add biasing to your sample, to your pattern, so make it a little wider or narrower if you recognize that during your exposure you find out like an overall offset in your exposed pattern. So there is a way more that layout beamer can do, but this is just the very minimum that you can you need to use to successfully transfer your sample to your pattern to exposure file. Now, when you import a file, I really suggest that in the GDS file, if you have multiple layers, you put in all the layers. So GDS system works with different layers and with different data types. So when you make your K-layout file that has like multiple layers that are exposed at different time, export everything. And I'm telling you why it's a good practice. It's because in that case, you can see your whole pattern imported into layout beamer. And it gives you a much higher control that your different layers, as you move through the conversion, will be exposed at the exact same coordinates. so your overlap and alignment won't be messed up. So, for example, I imported this file in here, and then after I importing it, you don't really need to change anything on this tab. You can see that there are like 3 different layers. From here, there are these red rectangles, which is just a zooming part of the center part of this bonding pressure. This is something that was done by optical lithography, and my nanoscale devices are going to be exposed by E-beam. But I actually imported into layout beamer all the optical lithography part, because then it will make setting up your CJOP file much easier. And then in the E-beam, the 2 different color has the 2 different layers that I'm exposing. Now, layout beamer can only convert 1 layer at a time, but so this is why you need to extract the layer, which layer you want to actually convert to the GPF file. So, for example, here you select the layer 57 from the previous slide. This is this blue layer, and then you are going to work on that one. I suggest to convert all of your files at the same time. So if you already know that you will have like 2 exposure, then first export the first layer as one exposure file, and then do your second one. From these 3, you only have to change a few parameters, like changing the extract layer and change the file name where it's going to be saved. And then you can be ensured that your alignment at least will be not off because of your pattern has different origin or different extent that makes some shift in the pattern. So I already talked about that. It's a good practice to import your whole layout into the layout beamer and extract 1 layer at a time to keep the origin and the alignment of your different layers. Now, the healing is somewhat important, especially if you are not very careful on your initial layout design. Because what it does, it actually removes all the initial fracturing that GDS does on your initial export. Also, if you, for example, you created your pattern let's consider that this diagonal part of the sample is extending a little bit here into the vertical rectangle. In that case, these 2 features are overlapping, and that is fine for you to look at. But E-beam will consider that you have like a pattern that goes up until here, and it also considers that you have a rectangle here. And this area where the 2 parts are overlapping will get double exposure. Now, if you are here on your large part of your sample that is just kind of like an electric lead of your devices, and you will have like a larger area, then it's probably not critical part of your sample, so you can fine with that. But consider that here in the center, the lines are around 50 nanometers. And if this horizontal line is actually overlapping with the vertical line, then here in the center, you will have like a double exposure. So it's not just you have the proximity effect, as Professor Bernstein discussed previously, you will actually have like a double exposure. So you can pretty much guarantee that 2 lines that you position very close to each other in the center will be overexposed and probably touching that you don't want to do that. So if you do healing, what the software does is actually look for all the overlaps and all the internal boundaries of your pattern, and it removes it. And then you can set up the fracturing yourself in the E-beam, in layout beamer, the way you like to do fracturing. So, and this fracturing is done in the export tab on this hierarchy. So in this one, this is the export, and this itself has multiple steps to condition your GPF file. So when you first open this tab, you can select the basic settings where you give your file name and you select the correct E-beam system. Now, when they do some software update, this might change how it actually named. Just look the email from Faye. He will tell you that which one to use, or look the documentation on your online on the Google Google Drive folder of the clean room. Also, you can see some summary about your main field, the current settings for main field and subfield, and the resolution. But these values will be changed or can be changed through these subsequent pages of this export tab. So the first thing that you have to consider is your main field size and your resolution, or more precisely is the grid size. So the electron beam that exposes your sample has a finite width. In our system, it depends on your beam current and the final aperture of the final aperture, and it can be between around 2 to 10 nanometers. Now, when you are exposing the sample, your pattern, this beam is actually moved like a raster scan. So if you want to fill this rectangle up, and then the beam step size is tell you that how far these shots are next to each other. So if you actually choose like a step size that is larger than your beam size, then it's most likely you will underexpose your sample. If you space them very close to each other, then it's most likely that you will overexpose your sample. So there is, you can do some design of experiments to find out that what is the appropriate energy and the beam step size to correctly expose your sample. So this is one variable along with the dose. And the other important part is the main field size of the beam. So the electron beam is lithography. The beam is, there is a beam deflector that can move the beam in a certain width without moving the stage physically under the E-beam column. And this area, which can be reached by the electron beam without physically moving the stage, called the main field. Now, the larger the main field, the larger the exposure distortion you can actually achieve. So if consider that, let's say, in our electron beam lithography system, we have a 20-bit deck, and each main field deflector moves the beam by 1 nanometer. So altogether, we can move the beam in a 1.05 millimeter area. So if you consider that this is the entire area that you can move the beam, obviously the center of the field which is right above the column, and as you deflect the beam and move to the side, you can actually increase larger and larger distortion in the beam shape, and therefore causing some issues in your exposure. So it's very important to find out your exact, to limit your main field size, what is viable for your pattern. This doesn't really add too much time on your exposure to move from one field to the other. The trade-off is that if you have like long patterns that are actually doesn't fit into one field, then you can have like stitching error. So as you can consider that there is like a feature that is one part is in one field and the other part of the pattern is in another field, the stage physically move between the two. If there is some error in the stage movement, then you can, instead of having like a single line, it can have break. So usually what you want to set up, and I show some example, make your not critical size in different fields, and whatever is a critical size, try to keep it in one field. Now, if you are fabricating like metasurfaces where you have like very small patterns exposed in a large area, then you probably have to make a trade-off between field size and stitching error. If you are doing some devices where you have like big interconnecting lines and fine nanoscale devices, you can actually select the field appropriately. So here are a few differences, but you can do considering in this field order. So for example, you selected your field size. In this case, it's like 240 microns. And then you have this 4 pattern that you want to expose. Now, if you pick the fixed settings, the beam is arbitrarily defines an origin based on your pattern, and then just fills it up with these 3 different fields, as you can see. The rectangle, this black line is the boundary of a field. So as you can see it, the way it set it up, the field size goes exactly through the critical part of the sample. So one field is the left one, some part of the devices will be exposed there, then the stage move, and then this part will be exposed. Now this device is fine because the whole device is in the center of the field, but this one is probably not going to be ended up well, or it will be like some different dimensions that you wanted to design. So you can pick floating, where the software is smart enough to try to find your pattern and center them around the field size. So for example, in this case, it automatically picks two fields and it's centered around these two devices and these two devices. It's still not perfectly ideal because your center of the field is on a blank space and your critical size of the device is here in the sides. So what you can actually do is you can actually, let's say, reduce your field size, what I did in this other exposure where I had even smaller samples. So for reference, this is 50 nanometer line for a few microns, and the whole thing is about 10 micron long with 2 micron width. Obviously, this narrow region is the most critical part of this exposure. So what I did is I set up the main field size to be 150 microns. I know that this is a smaller distance than any of the pitch in these devices. And so the system is kind of like forced with this floating setting to be around on one device. So each device has its own field. They will be exposed very identically above, will be on the center of the field. So the beam deflection will be very, very minimal. So you have the least amount of distortion. Now, if you have, let's say, like a large large pattern that goes out through millimeter, you can technically put them in one field. But considering that there are like, big lines like 5 to 10 micron wide lines, and also these nanoscale 50 to 100 nanometer wide, very short wires, that's not the best approach to do that. You can do it like, like a fixed or floating field to try to force the machine or the layout beamer to to assign the field correctly. But if you, for example, know that you have these simple blocks that build up your entire layout, you can actually manually, from your layout editor, you can export the center or corner of these blocks and then import it into the software. So in this case, what I did, I have like this 40 or 60 identical blocks that is critical to be in the center. So I uploaded the lower left and the upper right corner of the field that I wanted to have. And then the system is actually automatically adjusted this field. So each of these blocks is around one, centered around one field. And then these big lines, which are like, 10 micron wide, long interconnect lines, these are not a critical feature in terms of stitching error. So they can actually move a little bit to the left or right. It doesn't going to cause any issue. They will be still exposed. And if there is like a very small shift, that doesn't cause any issues. So this is just one of the tricks that I suggest to use. Now, the other part that you have to consider is that how you fracture the sample. So when the E-beam exposes the sample in a main field, it actually breaks down each of your pattern into small subfields that usually like a few microns, and then fill those patterns separately. Now, basically, we have like three mostly used fracturing method. There are the sequence and the shape detection. It's very rarely used. The conventional fracturing that breaks your pattern into rectangles and trapezoids. For the LRFT, it refers to large rectangles and fine trapezoids. Here, it makes the largest rectangles that can be fitted into your sample or your pattern. But wherever there is like a tapered segment or it changes like dimensions, it actually tries to resolve with very fine trapezoids to improve your pattern fidelity from your layout to your exposed pattern. This is usually more accurate if you have like tapered wires. Now there is a special feature if you are working with like circles or curved surfaces. Normally this is really hard to make in every lithography processes. So when you if you do like stepper, then when the mask is generated, this is where the curved and circles are an issue to make them correctly. And in the electron beam lithography, that remember that the electron beam is going in a raster scan, so it's not cannot really do like like a circular shape. So this is why it's kind of important for curves use the special curved fracturing method. And then you can also pick So you can actually pick like if you want to do a single pass exposure or multi-pass exposure. So in single pass, the beam goes through on your pattern only once, and it applies the dose that you set. This is fast and straightforward, and this works most of the case. If you have, let's say, have like a sample where it is prone to charging, and you can actually use a multipass where the beam goes through multiple times on the same pattern, but it doesn't apply the full dose at once. So if you have some conducting path or on your sample then it is possible to reduce charging on that way because you don't get exactly you don't get the full dose all at once, or the charging is just going to be more neutralized. But I never really use that. Probably some people need to use it. So this is the subfield that I mentioned, that the beam is actually layout beam and is fracture your pattern. So these are the subfield, these rectangles, and then it makes some fine trapezoids all the way on your sample. So these narrow lines is just simple rectangles. Now here's the difference if you have like curved or circles. So this is the conventional fracturing that uses this, it tries to fit these rectangles and trapezoids everywhere. For the large rectangles, fine trapezoid, that's probably a better. It's very similar approach in terms of like the edge of the circle. But as you can see, for the special curved fracturing method, makes a much finer subfields on your edge of this pattern. So your circle is resolved much better, and you will have a more your pattern fidelity will be more accurate than your as to your layout design. Now, finally, you need to set up the extent, and you can do it in an automatic way when the extent is actually the bounding box of your pattern. Now, this is where most people can get confused if they have like different layers and they are not exporting them at once, or they are because in that case the bounding box can be shifted left and right, especially if you use the automatic method. And then your alignment, when you export your files, it places the origin at different spots. And so at the end, what you have ended up is your pattern looks fine. Your features are in the center of the field or how you set it up. But when you import the pattern into CJOB to create your exposure file, you will notice that, or in worst case, after exposure, you notice that your alignment is very off. So if you actually have your full bounding box, your full pattern imported in layout beamer, then it gives you the coordinates of the entire pattern. And if you use the same number for each of your different layers, then you can ended up with the you will ended up with the right origin for each different layers, and they will be matched in your exposure. Now the last tool is the tool configuration. You really don't have to change anything. I'm not even sure that maybe you cannot even change the values. Just leave it as it is. So after you have your file, your patterns, then you need to create a CJOB file that is a script file that tells the e-beam system that how to expose and which order and where to place it. So the first thing is that if you are working with small chips, like small silicon pieces, quartz samples, whatever, not like wafers, then you have to give the width and height of this substrate. Now, here is a trick. So the E-beam E-beam has a height measurements to make your chip to be on the focal point of the crossover point of the beam. So this is where the beam is the narrowest. And to get the best exposures, but it needs to measure the height. And by default, the system measures the height, the largest area of your sample or your substrate as you defined in the system. However, if you can see that the height sensor is a laser that is incident in one end, reflects back on your sample, and then detected by the detector. Now, if you have like a thin sample, like a silicon chip, which is around 500 microns, this is held down on the table by clamps that are a few millimeters thick. If you are at the very edge of your sample or substrate, it is possible that this beam is somehow get blocked and the height sensor just doesn't able to measure the reading here at the very edges. What you can do is actually you give a smaller size in the system than your actual substrate is. In this case, the system reduces the area where it measures the height, and so it has a higher chance that you won't get a height error. Now, this is the part that we can. The other part that I think many users get confused about the alignment, that how to use the alignment marks. Now, if you don't have to do any alignment, then you are lucky and you just need to give a coordinate that you place your pattern in the center of your substrate and then you are done. However, if you have alignments, there are two ways to use the alignment marks in the system. You can do a hard way where you actually, you need at least 3 alignment marks to get a good alignment. So 2 for X and Y and the third for rotation. And in one way, you need to identify all 3 alignment marks in the system, and you have to find them in the alignment microscope, write down those numbers, and when you start your exposure, you have to use all 3 numbers after you find it in the system. Now, this gives you some extra work, and also, more importantly, each time when you find the markers just to get the coordinates, you expose the resist. So you can introduce extra proximity effect. You create like an extra background dose on your sample. So a much better approach is if you use a pre-marker. In that case, you only need to find 1 alignment marks. You tell the system that this is your pre-alignment mark, and then the system automatically knows that where to find all the other alignment marks. In that case, you just only need to find 1 mark in the alignment microscope and use 1 set of coordinates in the exposure. So this is how it looks like, that these crosses are the different alignment marks for each patterns. And then in this particular case, this is my pre-marker, that it has this particular coordinate system. And based on that, the system knows after you tell them that where are the other alignment marks, you only need to find this pre-marker in the microscope and starts the exposure on here. And then the system will find all the other patterns. Now, this layout tab, you probably know that allows you to set up different patterns. So you can set up, like these 3 different colors are different patterns. You can set up that allows you to expose different patterns, or you can use different beam currents or doses for the different patterns. So, for example, if you want to make like a contrast curve, you want to have like different doses, and then you can set it up here. Now, this is where you can also add like an extra pattern alignment mark. So the system uses global layout and pattern alignment marks. What it means that if you use like a global or layout marker, it just do 1 set of alignment mark search. So for example, let's say these 4, and when it goes to the different patterns, it doesn't do any extra alignment. If you actually set up pattern alignment marks for each and every pattern, it will do a pattern alignment as well. And finally, if you want to make sure that if you have like different layers, this is some trick that you can use to find out that your exposure, export of your pattern was correct. And so you can identify before exposure if your alignment will be fine. Just duplicate one of your pattern on the same die in this particular case and put the second layer on it. And then zoom in and see if your pattern is overlapped as intended by your original layout. Whatever you see here is what you're going to be exposed. So if you see that your pattern is shifted, then your exposure will be shifted. So it's better to correct it now than get a surprise after you develop your sample, your patterns. Now, in terms of resist, I don't want to get into too much details on here because Professor Bernstein already mentioned that there are two types of resist, the negative or positive, well, how you call the polarity in E-beam. Usually this is called negative E-beam resist, and PMMA is called positive E-beam resist because it's the direct right, and where you expose it removes the sample, but it's just polarity. You just need to know what it has. So there are two types of resist, PMMA, MMA, PMGI. These are way more common to use in E-beam lithography than negative resist, but negative resist does exist in electron beam lithography if you want to do some etching. Now, what I would suggest, if you haven't done it before and you do lift-off, is to consider to use like double layer resist structure. What double layer resist structure means is that you have like two different resist spin on top of each other. And you want to do that for lift-off because you want to have an undercut. So when you deposit your metal, you don't want to have any metal deposited on the side walls of your PMMA, because after lift-off, you will have ended up with rabbit ears and sidewall deposition that, especially if you have like a second layer, your metal will be break. So what you want to have is an undercut in the resist. So then you will have like a very nice trapezoid shape of your evaporated film, for example. For this case, you can use MMA and PMMA. The MMA has a much lower molecular weight than PMMA, so it is much easily damaged. This molecular chains are much easily break by the E-beam resist. And when you're using the same developer, then you develop all at the same times, and you will get a larger undercut because more chains are broken. So your developed area will be larger. Now, one of the best developer to develop PMMA and MMA is using this IPA, MIBK, MEK mixture with these ratios. This is particularly was developed by Professor Bernstein and his students. This is a very high contrast developer for PMMA. This works really well. It's very stable. All of these chemicals are available in the clean room, so you can mix your own mixture and use it. Doesn't require any cooling. If you cool it down, do core development, then you can get a little higher resolution if you want to. But if generally, if you are not on the cutting edge of the machine, but like a 20 to 50 nanometer range, then room temperature developing is perfectly fine. The only downside of using PMMA and MMA is that you develop the resist at the same time, both resist, and you don't have too much control on the undercut. The MMA has a fixed molecular weight, and you cannot really control how much the undercut is. The other approach is if you use PMMA and PMGI. PMGI is not provided by the lab, same as for MMA and PMMA. You need to buy your own, but the good thing on that one is that you can develop your PMMA and PMGI layer separately. And what the PMGI layer developing is actually a etching, not really a developing. So what it happened, but the developer that we are using for this AZ917 is it etches very fastly, and the duration you dip into your sample in the developer determines this undercut. So for a shorter dip, you will have less undercut. For a long dip, you can have a much wider undercut. So if you need to control your undercut, using PMGI is a much better approach. If it etches your PMGI layer too fast, the pure AZ917, you add a little DI water to it to slow down this etch process. And after you develop your sample, before metal deposition, I highly recommend to use like a discamming and oxygen plasma. All it does is if some little scum, it's not even a layer that remains on your substrate. It's, you know, like maybe some patches of resist where your resist, especially if it's not the newest one, you know, these molecules can crumble up and they became a much larger molecule than originally intended to be, which is not exposed by the resist, and it just stays on the openings. So you want to remove that with some oxygen plasma. Now there is other thing about like charging. So if you have like charging sample that is not conductive, and you expose it with electron beam then charge accumulates on it, and then due to the repulsion force, the electrons will be repulsed, and it will be spread out in a much larger area. Now, obviously, this results in pattern distortion, and in order to avoid that, you have like two different options. You can place a metal layer on top of your resist. In this case, it's a thin layer, like, you know, typically 10 to 20 nanometer chromium. The only downside is that you have to do thermal evaporation, because the E-beam evaporator can expose your resist and makes your doses off compared to not having, so it's basically pre-exposes your resist. But in that case, the metal serves as a conductive layer, and you can avoid charge. The other possibility is that you place a metal layer, if your process allows, underneath the E-beam resist. In that case, you can also avoid charges. Now, there is a third option. So the issue with this one, this is commonly used here in Notre Dame. I know people who are using this one, that before you develop your sample, you have to remove your metal layer. The other option is that you can use e-spacer. This is like a water-soluble compound, so it's much easier to remove. You can apply it top of the resist, and you can just spin coat it, so it's obviously much faster to do that. But the downside is that it's pretty expensive. It's around $3,000 per 100 milliliter. So you can consider this one if you have, like, you know, like a quartz or a glass substrate, and you are doing a lot of this exposure, and you have really charging issues, then probably it's worth to invest for e-spacer. Now, I want to finish it up with two tips and tricks that most new users have issues with the E-beam, is to set up your height and your rotation alignment on the physical stage. So when you place your substrate on the stage, and in this case, we're going with an example with the table for small samples. So you use like these two clamps to fix your substrate there. And what you have to do is you have to set the height of this table to match to the marker chip. And then you have to make sure that your substrate is very close to the XY coordinate system of your of the tool, because the tool can do some rotation adjustment, but not much. So in order to adjust the height of this table, you have like 3 adjustment screws. And in order to make it efficient, what I suggest to use is that use 3 points on your substrate to measure the height, and only adjust the screw that is closest to the laser spot where you're currently measuring. So for example, you measure the height on the marker chip with this in the alignment microscope that is in the E-beam preparation, simple preparation room, to be 18 micron, let's say. Move your laser dot on this upper left edge of your sample, and try to adjust the screw, just this one, to bring it closer to the value. Then move to the next spot and adjust this position, and then move somewhere here in the middle and adjust this adjustment screw. If you do like this iteration, that you go up, go in let's say in a circle, then you can very quickly find the right height. Usually you can get it within 1 micron, or even less if you have experienced, but I think within like 2 or 3 micron, everything should be fine. So this is one of the easiest trick that you can do. And the other thing is the rotation alignment. Now, when you normally you do the rotation alignment after you set up your height, and in the rotation alignment, use 2 alignment marks, or you use 2 features on your sample that are in one lane on the x-axis. So, for example, there are 2 gold alignment marks on this cartoon. And what you want to do is that use one set only for adjusting the rotation and use the other set only to adjust the X and Y shift. In that case, you can get a very quick adjustment in rotation. So for example, in the first step, make the crosshair on the alignment microscope aligned with the edge of this square of this alignment mark, and then move to the other alignment mark, but only using the X knob on the stage control. So just move it there. Then you will probably end up something like here, that the X is a little lower and it's a little left from the adjustment mark. Then make a small change on the table rotation to move this cross closer to your alignment mark. You don't have to be precisely there because maybe you can overcompensate it if you have like a huge rotation error at the beginning. So just bring it somewhat closer, but only change the rotation at this point. And then using the X control on your stage, move back to your first alignment mark. Set it up, again, using only the X and Y position. So make it align with this one, like here. And then repeat the steps. So move back again using only the X control to the alignment mark, and then make a rotation adjustment. And so if you do this step repeating, that you only adjust rotation, let's say at this mark, and XY error on this mark, within like a 2 or 3 iteration, you can be very close that when you move from the 2 alignment marks, the edges of the alignment marks will overlap. And I think this is my last slide. And if you have question, I think it's the same as Professor Bernstein mentioned, that reach out to me via email, and I will be happy to answer those.